Hello everyone, I hope you're doing well. Today we're going to be continuing our exploration of systems of differential equations, and we're going to be focused primarily on the different phase portraits that may arise for linear systems of two ordinary linear differential equations. So let's just quickly go over some of the basics that you definitely should know when trying to draw the phase portrait for a linear system. So once we have this linear system, obviously writing it into matrix form definitely will give you a little bit of an advantage. So let's write this as xy prime is equal to 2 5 minus 1 times xy. So I'm going to be referring to this coefficient matrix as A. Obviously, this isn't a time-varying matrix, so all of the eigenvalues and eigenvectors will remain the same for all points in the time phase of our solution, which makes things a little bit easier. But even if this is a matrix of time, keep in mind we do have the theory of linear time-varying differential equations, where you can find that the fundamental matrix is just going to be equal to the exponential of the antiderivative of that time-varying matrix little a, right? So we obviously do have some theory for time-varying systems, but let's assume that it's a constant matrix always, or at least a constant matrix for a particular point in time. So once you have identified your matrix A, then you can find that one of the eigenvalues, once you find the characteristic polynomials that equal to 0, you're going to have eigenvalues 4, and you're going to have also -3. And from these eigenvalues, you can of course find your eigenvectors. For lambda is equal to 4, one can find that C1, 1, 1 will work, and another eigenvector C2 to -5 will also work. So a couple things that we need to analyze now once we try to decide what type of phase portrait is going on is what's going on with these eigenvalues. So in this case we have that all our values are real and they're also opposite signs. In this case we have one positive, one negative, and the imaginary part for both of them is going to be equal to 0. Right? So that's going to be important later on. So, aside from those little comments, we can state the actual solution to be xy is equal to c1, 1, 1 times e to the 4t, and then plus c2 to -5 times e to the -3t, and that would be the solution to our system of differential equations. So, it's also very important to note that the critical point, of our system is going to be the point 0, 0. So that's where the gradient of our vector valued function is going to be equal to 0. Or you can just set x prime and y prime both equal to 0 and find out xy that makes that true. So if our eigenvalues are both real and opposite signs, then we can classify this critical point as what we call a saddle point. So how did we graph the phase portrait associated to systems of differential equations that has a saddle point? So the first thing that we need to do is first graph our eigenvectors. So let's start off with 1, 1. So 1, 1 is going to be along the line y is equal to x. Let's also draw a dotted line so it doesn't cross over with our solutions. So there's our y equals x, or 1, 1, which I'll call. Let's also not put arrows at the end, but let's call this V1. So it's going to be V1. And then V2 is located there, so I'm going to go over 2 and down 5, so somewhere around here, let's say. So let's assume that this is our second eigenvector. Let's call it V2. And there's our critical point located at the origin. So what do we have here? So as t goes to infinity, notice that this is going to vanish to 0 as t goes to positive infinity. And notice that this term here is going to vanish to 0 as t goes to minus infinity. So if we go from minus infinity to positive infinity, we're going to be traversing from vector 1 into vector 2, right? So what would that phase portrait look like? So let's pick a couple points. So we have 4 quadrants to sort of analyze, and also those axes of those eigenvectors. So as t goes to infinity, v2 is going to vanish and v1 is going to dominate. So we're going to be getting close to v2 or close to v1 and far from v2. So we're going to have this type of pattern here. So again, close to v1, away from v2. So we're going to have that traversion there. And again, close to V1, away from V2. Close to V1, away from V2. Similarly, on these axes, we have going that way towards V1. And again, away from V2, the origin is included in that. And we also have the critical point, or the stationary point as some people may call it, that doesn't move, which is the point 0, 0. So that would be the phase portrait associated to a linear system that has a saddle point at that point 0, 0. Okay, so again, this is the type of phase portrait you're always going to have when you have two eigenvalues, lambda 1 less than 0 and the other positive. Right? And that's how to determine what the actual solutions are going to look like. So that is critical point type 1. So this would be a saddle point. Now let's look at the next easier to identify phase portrait, where, for example, we have a couple cases. A, both are negative, and both are positive. Let's make them both equal to each other and positive. I'll draw a couple scenarios here. Let's call it like A1 and A2. Lambda 1 less than lambda 2 less than 0, and then the B1, B2. Let's do 0 less than lambda 1 less than lambda 2. They could be equal to each other, need not be though, but as long as both are positive, both are negative, you're going to have the following phase portraits. So I'll do A1, A2, and B1, B2. So if all of our eigenvalues are negative, so if we sort of go back up to our solution here, so let's sort of pretend what we have here. Notice that our eigenvalues are always going to be located in those little exponents, right? So now we're going to pretend that both of them are negative, not just the -3, but let's pretend that's a -4 instead of a +4. So as t goes to infinity, both those vectors are going to go to 0, 0, and xy is going to get close to 0, 0. And if both of them are positive, we're going to be getting away from 0, 0, obviously at potentially different rates. So if our eigenvalues are both equal to each other and negative, what you're going to have is that your solution vectors, or your phase lines, are going to be going in these directions. So they're all going to be pointing towards the critical point, which is 0, 0. And obviously, if you have coefficients that are not necessarily equal to each other, but still both negative, then it's possible that these flow lines are sort of, pointing downwards or pointing upwards towards 0, 0, right? So that's one possible case that you could have. You could also have a different orientation. You could have this one and that one, this one and that one, this one and that one, and this one and that one. Also, the eigenvectors for each of these two pictures are 1, 0 for one eigenvector and 0, 1 for the eigenvector, but you could rotate this picture where you have different eigenvectors that are not the unit vectors along these principal axes, but still having your negative both eigenvalues. So all of these points in some sense have the same exact behavior. They're all converging to the one and only critical point. This is usually called a stable node. Some people will also call it a sink. Right? A stable node or a sink. Now, if both of them are positive, and let's assume that they're positive equal to each other, then what you're going to have is you're going to have these linear trajectories, right? So it's no longer a sink because the points aren't going inwards, they're now going outwards. And of course, they can go outwards in different directions. For example, you could have this as your phase portrait. You could also have the other one, where you have this, 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 and that. And in terms of which one is which, it depends on which one is the dominant eigenvector. So for example, in this picture, all of the points are sort of tilting more towards the eastwards direction rather than the north. So that means that eigenvalue, for example, that could be associated to eigenvalue is equal to 5. This one still, it's pulling it that way, but it's not as large. So that would be like an eigenvalue is equal to 3. And this would be like an eigenvalue 3 and an eigenvalue 3 type of picture. Right, and over here, this could be like a lambda is equal to -2, lambda is equal to -2, and over here we have like a lambda is equal to -5, and a lambda is equal to -1, for example. Right, so that's pretty much the different cases that you would have when you have your eigenvalues of both real and the same sign. So your two negatives will be your stable node, which would be also considered as a sink. And over here we have what is commonly called an unstable node. Some people also refer to this as a source, right? A source of energy and a sink of energy, right? So that would be the second type of critical point that you could have. So we either have a sink, a source, which both are referred to as nodes. We also have a saddle point. So let's actually look at an example and see if we can draw the phase portrait for this particular system. So let's assume that we have x, y prime is equal to -2, 1, 0, -2 times xy. If you want to pause this video and see if you can find the eigenvalues and eigenvalues for this, eigenvalues and eigenvectors, I recommend you doing so. But once you do solve them, you're going to have that lambda 1 equals lambda 2 are both equal to -2, and you're actually going to have only one reasonable eigenvector, in particular 1, 0. And for the other, you can choose practically any other eigenvector because you won't be able to span the entire eigenspace because the nullity is going to be equal to 1. So what you have here for the solution, xy, this is going to be equal to c1, 1, 0, times e to the -2t, and then over here we're going to have c2 times some vector times t e to the -2t. So what I'm going to do is I'm just going to choose my free variable to be whatever I want because y is going to be my free variable. So I'm going to choose that to be 1. So 1, 1 is going to be my other eigenvector. As long as you choose an independent eigenvector from that one, then life is going to be good. Okay, so once you have your two independent eigenvectors, and keep in mind it's t times e to the -2t because we had a repeated eigenvalue that comes from second order differential equations. Same theory applies here. Let's also think about what that curve looks like and that curve looks like, because as t goes to infinity, keep in mind that sort of goes down like that. But for t e to the -2t, it doesn't really have that picture because we actually have a local maximum and then it eventually goes to 0 there. So we get a little bit of far. We hit 0, then we get far, and then we get close to 0 again. All right. So what actually would this look like? So if we just analyze our two eigenvalues, what we have. Well, this is obviously going to be a stable node or a sink, right? But what type of sink? Because notice that our trajectories are not necessarily exponential because of this t e to the -2t, but it still is going to have a stable node sink pattern, right? So once you have your first vector, v1, so this is my dominant, our first eigenvalue, what you're going to have is that you're going to have your curves sort of swing in to that particular eigenvector, right? So everything's sort of going to be pulled towards that vector. So let's sort of make them asymptotic to each other. Right, so these are going to sort of swing into each other. So that's practically what you're going to have on that phase. And obviously over here, they're going to sort of pull in. Right? So that's pretty much what's going on there. So obviously they're still going into your particular critical point 0, 0, but they're going in there in that curve linear fashion. And the reason it has this curve linear fashion is due to that repeated eigenvalue, but again, it's still a sink because both of our eigenvalues are both negative. Now that we know how to analyze systems if the critical point is a saddle point, or if the critical point is a node, which could either be a source or a sink, now we're going to look at the third type of critical point, which is, it's going to be an interesting type of picture. So as usual, we're going to be looking for our eigenvalues. For this particular case, we're going to have our eigenvalues to be 1 plus I, and our second is going to be 1 minus I. And one can find that your associated eigenvectors are going to be C1, I1, and C2 minus I1. So those are going to be your two eigenvectors associated to your two eigenvalues. So notice that what we have here is we have complex eigenvalues. For saddles, sources, and sinks nodes, notice that both of them were real, either both positive, both negative, or opposite signs. So when we have this, well, what does our solution look like? Because this is a little interesting. So our solution will be equal to C1, I1, e to the 1 plus I, t, and then plus C2 minus I1, e to the 1 minus I, t. What I want to do is I want to distribute this t into this parenthesis, and please don't forget the t. That's going to give us C1, I1, e to the t, e to the it, and then plus C2 minus I1, then e to the t, and then e to the minus I t. Now what's going on with this I stuff? So you may remember that e to the I theta will be equal to cosine of theta plus I sine of theta, which is sometimes referred to as the Euler-Cotes identity, and the proof of that via Taylor's series is pretty straightforward. So using that identity and the fact that cosine is an even function and sine is an odd function, what we can do is we can re-represent our solution in terms of sines and cosines. So we grant this as C1, I1, e to the t, times cosine of t plus I sine of t, and then plus C2 minus I of 1 e to the t times the cosine of t minus I sine of t. Now, let's see if we can analyze the solutions for this. So as t goes to infinity, notice that e to the t, that's going to go to infinity, and this is going to go to infinity too, but it's going to go there in a periodic way, because sometimes cosine plus I sine is going to be negative, sometimes it's going to be positive, but it's still going to try to grow very, very big. It's just going to switch directions, right? Is it positive infinity or negative infinity? It's still getting big. It's just changed in orientation. So in particular, what type of orientation is it going to be? So remember that x prime, y prime was equal to x minus y and x plus y. That was our original system. What I want to do is I want to choose a particular point of reference. In particular, I want to focus on xy is equal to 0, 1, just to sort of get a sense of where and how I'm getting to that plus or minus infinity. So at that particular point, x prime, y prime at 0, at that particular point 0, 1, that's going to be equal to 0 minus 1 and 0 plus 1, which is going to be equal to minus 1, 1. So at the point 0, 1, which is up here, I'm going to have a velocity vector of minus 1, 1. So that's going to be equal to minus 1, 1. So I'm going to be pointing in that direction. So if I'm going to be spiraling around my critical point 0, 0, then I need to be getting into that particular point at that particular gradient, right? And then obviously I should be spinning in some direction in that form. So with all of that in place, then I'm going to have that my phase portrait for this particular situation where I have my eigenvalues lambda 1 and 2 is equal to 1 plus or minus I, I'm going to have this beautiful phase portrait, right? Which some people refer to as an unstable spiral, or some people also call it a spiral source. Right? And the way that I figured out which direction it was moving is I just took a particular point and determine, which way was it going. Like, is it going that way, or is it going that way at that particular point? And keep in mind, 0, 0 is still a critical point for this particular system. And could you have the other direction? Of course, for example, you could have this particular situation. Again, let's assume that our velocity vectors are going outwards. That would still be an unstable spiral or a spiral source. And what happens when you have the other directions? Like, could you have this picture or this picture where instead of going outwards, we're now going inwards? So inwards, right? In this case, yes, right? So these pictures will be referred to as stable spirals or spiral sinks, right? So how do you know the difference between a stable spiral and an unstable spiral just by looking at your eigenvalues? So for our eigenvalues, we had lambda is equal to 1 plus or minus I. And these can be demonstrated by having eigenvalues y. Lambda is equal to minus, let's say, 3 plus or minus 5i. And the key thing you need to notice here is that that t, because remember we had e to the t times that e to the I theta term, that's just our periodic nature, but we had a real part of 1, and that's what was making it get really, really big. So if our real part of our eigenvalue is negative, then both of those ei theta and e minus I theta terms are going to decrease to 0 as time goes to infinity, right? So you will have a stable spiral or a spiral sink if the real part is negative, and you'll have an unstable spiral if the real part of that eigenvalue is positive. And keep in mind, for both of these situations, it was only true because the imaginary part of your lambda value was not equal to 0. In this case, it was 1, or in this case, it was 5. So that's the next type of phase portraits that we could have. Now the question becomes, okay, well, what if you have a complex eigenvalue, but instead of the imaginary part being non-zero, what if it equals 0? So to guide this next portrait, let's assume this system of differential equations, x prime equals minus y prime equals x, very simple system to deal with, which is going to be transformed into the form xy prime is equal to 1 minus 1, 1, 0. What's that 1 doing there? That needs to go away, right? Times xy. So this is going to be our system. So obviously we need to find the eigenvalues and eigenvectors of this matrix A. And one can find that lambda 1 will be equal to I, and lambda 2 will be equal to minus I. And one can find that the eigenvectors, if you really need them, are going to be equal to I1 and minus I1, and any scalar multiple thereof. Right? So notice that we have complex eigenvalues, and the real part is equal to 0. So it's not going to be a spiral, it's not going to be a saddle, and it's not going to be a node. So what's it going to be? So let's look at our solution and see if we can understand it there. So xy will be equal to c1 I1 times e to the it plus c2 and then minus I1 e to the minus it. And now let's use our Euler-Cotes identity for this to transform. So c1 I1, and then we're going to have cosine t plus I sine t, and then plus c2 minus I1, and then cosine t minus I sine t. Let us decompose this solution into its x and y components and analyze there. So once you rearrange everything, what you're going to have is x of t is equal to c2 minus c1 times the sine of t plus I times c1 minus c2 times the cosine of t. And then y of t is going to be equal to c1 plus c2 cosine of t. And then plus I times c1 minus c2 times the sine of t. So for finite t, we can only graph the real part. So this first portion of x and y is the only thing that's going to be related to us in the xy phase portrait world. So what type of curve is this? Keep in mind this is a parametric equation, but this should look familiar as just an ellipse. And one can actually verify that for our particular problem, it's actually going to be actually, let's just not say it's a circle, but it's an elliptical curve. That much is certain from this. So since, again, 0, 0 is a critical point, what would our phase lines look like for this? So if it's an elliptical world around 0, what we're going to have is something that looks like this. Now we just need to figure out what is the orientation for this particular curve. So keep in mind x prime was equal to minus y, and y prime was equal to 1. So let's choose again the point xy is equal to 0, 1 to get a point of reference. So when x is equal to 0 and y is equal to 1, we have minus 1, and y prime will be equal to, where'd my x go? That should be equal to 0, right? So with that in mind, so at this particular point, which way are we pointing? So we're pointing to the vector minus 1, 0, which is the negative x-axis. So we're going to be pointing in that direction, which means that these orientations are going to be counterclockwise. Right, so counterclockwise rotation. Right? So this is not a spiral, it's not a saddle. This is what we refer to as a center. Fair? So it's a center of some periodic path. Periodic path. Right? It could be an ellipse, it could be a circle, and for the nonlinear case, it's just going to be some closed path with some center and some realm of realisticness in the middle of it. Right? So this type of phase portrait is associated where your eigenvalues are both complex, but the real part is equal to 0. And if the real part was not equal to 0, then we'd have either a spiral source or a spiral sink. So up to this point, we have considered 4 different types of phase portraits that we could get. And keep in mind, all of these were associated to the case where we have one critical point, which occurred at 0, 0, at least for our examples. But keep in mind, it's not necessary that the critical point is located at the origin, i.e. where your eigenvectors are going to intersect. Let's look at a very easy counterexample to the fact or the claim that 0, 0 is always a critical point for a linear system. Let's assume we have x prime is equal to ax plus by plus alpha, and y prime is equal to cx plus dy plus beta, where alpha and beta are not necessarily equal to 0. So what we have here is an inhomogeneous linear constant coefficient matrix system of differential equations. Agreed? So our critical point still exists where the gradient of our system is going to be equal to 0, right? It's not going anywhere in any direction. So where is that going to be true? So this is true, keep in mind, if and only if x prime and y prime are both equal to 0 simultaneously. So we can solve this system to be equal to ax plus by, cx plus dy is equal to minus alpha and minus beta. So keep in mind this coefficient matrix has a nice determinant of AD minus BC. And then we can use Kramer's rule to find where that x and y is located. So that means the x-coordinate of our critical point is going to be equal to the determinant of minus alpha minus beta BD all over AD minus BC. And the y-coordinate of our critical point will be equal to the determinant of AC minus alpha minus beta all over AD minus BC. So that's where the location of our critical point is going to be located. And it's very easy to see that if alpha and beta are both equal to 0, then the determinants of those tops are going to be 0. And then that's just going to give us the origin as our critical point, which is what we had before. And keep in mind, this is only true in terms of unique critical points if and only if the determinant of that coefficient matrix is not equal to 0. So a natural question is, what if it is? So what if the determinant of our coefficient matrix is not equal to 0? Is it possible that we have infinitely many critical points? Might sound weird, but let's look at an example and investigate. So let's assume we have xy prime is equal to 1, 1, 2, 2 xy. It's clearly the case that this determinant is equal to 2 minus 2, which is indeed equal to 0, which might cause a concern. But we can still find eigenvalues of it. That's not a concern. So let's find our lambda 1. One can find that one of the eigenvalues will be equal to 0 in this case, because if the determinant is equal to 0, one very important property about determinants is it's actually equal to the product of its eigenvalues. So if you have the determinant is equal to 0, that means one or both of those eigenvalues are going to be equal to 0. Right? So in this case, 0 is one of the eigenvalues, and 3 will be the other. One can find that the eigenvector for 0 will be equal to 1 minus 1, and the eigenvector for 2 will be equal to the vector 1, 2. So in terms of the vector that we need to understand for this phase portrait, we need to focus on this one. This is the very important one, and this other is going to help us decide directions of the rest of our phase portrait. So what we're going to do is first realize that we're actually going to have infinitely many critical points. In particular, any vector, any points along this eigenvalue of 0 actually will not move. And you should be able to verify that with a little bit of linear algebra. So if we graph 1, negative 1, and all its scalar multiples, so this is going to be my v1 and v2, any critical points, or any points on this line will not move. Now, this other line, or vector 1, 2, that's going to allow us to decide where our other vectors are going to be going. So 1, 2, let's give it a little bit of accuracy. So that's going to be this point. All of our other solutions are going to be pointing in that direction. And all other values will also be pointing in that direction, because I just chose 0, 0 as just a reference point, but there's infinitely many reference points that I could choose. So instead of choosing 0, 0, I could choose minus 1, 1, and I could get those solutions. I could get those solutions, and practically any of these solutions. Right? Oh, that arrow is going in the wrong way. It should be going away from our line. So this line has a name. It's called a line of equilibria. Equilibria, or equilibrium. Because we have many points that do not move, so those are our equilibrium points, but we have infinitely many. Any point on that line will have a gradient of 0. Fair? So that gives us our phase portrait. Now question, how do we know that our curves or our trajectories move outwards? You can easily determine that via the other eigenvalue. So if that is our eigenvalue, it's positive. Obviously, whatever phase portrait it is going to be unstable. So this is usually what we refer to as an unstable line of equilibria. And if we had a eigenvalue that is negative, where one of the others would be equal to 0, let's assume that this is our line of equilibria, but let's assume that our other eigenvalue is like minus 2. Then it's possible that our phase lines would be looking something like this. Keep in mind these lines need not be perpendicular to that other line of equilibrium, right? It's dictated by that other eigenvector that the non-zero eigenvalue is associated to. So this would be the fifth type of phase portrait that you could get. And there's one extreme case of a line, quote unquote, of equilibrium, and that's when you have that lambda 1 and lambda 2 are both equal to 0. And I'll let you explore that on your own and what that phase portrait would look like. But for the 2 by 2 cases, that covers every single scenario of eigenvalues that you could encounter and all of their phase portraits presented. Hope you enjoyed this video, and I'll see you in the next one where we're going to be taking a look at some nonlinear systems and their phase portraits. Hope to see you there. Take care.